Good day everyone. Today, we begin our journey in one of the most important foundations of computer science, algorithm and complexity. This is chapter 1 of our course, and throughout this presentation, we will explore the algorithms, why they matter, and how we can evaluate their effectiveness. Whether we realize it or not, algorithms are behind every software, mobile app, or system we interact with, from how Google sorts search result to how Facebook suggests new friends. Understanding algorithm is a key to becoming an effective computer scientist or software developer. Let's start with the basics. An algorithm is a set of clearly defined instructions that tells a computer how to solve a problem or perform a task. For example, when you cook using a recipe, you are following a real-world algorithm. The recipe takes in ingredients, yun yung input natin, performs a set of steps, will be your processing, and ends with a dish. Yun naman yung ating output. Now, complexity refers to how efficient an algorithm is. We usually measure this in terms of time and space. Time complexity deals with how long an algorithm takes to run as the size of the input increases. Space complexity refers to how much memory or storage it uses. So, when we say that an algorithm is efficient, we mean that it solves the problem quickly and uses as little memory as possible. Understanding these two concepts, algorithm and complexity, is crucial in determining which solution is best for a given problem. To elaborate an algorithm, we must have three main parts. It must accept some form of input. It must process the input through a series of steps. And finally, it must produce an output. Let me give a simple example. Suppose you want to find the largest number in a list of 5 numbers. A basic algorithm would, number 1, start by assuming the first number is the largest. 2, compare it with the next number. 3, if the next number is larger, update your assumption. Number 4, repeat this until the end of the list. And number 5, finally output the largest number. This is a simple yet effective algorithm, and it shows that algorithms don't always need to be complex to be useful. Now, not all algorithms are created equal. A good algorithm must satisfy several characteristics. First is correctness. It should always give the right answer. If your algorithm to find the largest number fails when the largest number is at the end of the list, then it is not correct. Second is efficiency. It should run in a reasonable time and use minimal resources. Imagine an algorithm that takes 1 hour to sort just 10 numbers. That would be very inefficient. Third is finiteness. It must have a clear stopping point. If it keeps running forever, then it's not a good algorithm. Ibig sabihin, ang algorithm natatapos. Fourth is definiteness. Each step must be clear and unambiguous. Malinaw dapat. For example, saying sort the list is not clear unless you define how you are going to sort it. Finally, it must handle input and output properly. It must accept data, process it, and return a result that solves the problem. So, hindi enough na sabing, maghugas ka ng pinggan. Aba, kaya nga lagi ako napapagalitan ng asawa ko. Naghugas nga ako ng pinggan, pero gina-expect pala niya, lilinisin ko rin yung lababo. So therefore, algorithm must be clear. Walang manghuhula ka pa, dapat malinaw. Algorithms can be represented in different forms depending on the situation. The most basic way is through natural language, which is how we just described the find the largest number example earlier. But natural language can sometimes be too vague or ambiguous. Ibig sabihin, itong normal na nag-uusap tayo, pwedeng yung instruction ko is hindi talaga ganun ka-specific. Lalo na tanungin mo ang Pinoy, saan ba papunta sa Quiapo? Sumakay ka ng ano, tapos punta ka dun sa ano, tapos baba ka sa ano. Puro ano na lang no? So, para ma-avoid natin ang confusion, then pwede tayong gumamit ng pseudocode, which looks like programming, but is not tied to any specific programming language. For example, max is equals to first in the list. Now, for each number in the list, then if number is greater than max, then max is equals to number. This is clearer and easier to translate into an actual code. Finally, we have flowcharts, which use visual symbols to represent processes, decisions, and flow of control. These are especially useful for planning and explaining logic before writing any code. All three natural language, pseudocode, and flowcharts are valuable tools in designing and understanding algorithms. Let's now discuss why algorithms are so important in computer science and beyond. First, algorithm gives us a step-by-step method for solving problems. This is a crucial when we want our computers to perform tasks reliably and consistently. Whether you're building a calculator app or a self-driving car system, the underlying processes are driven by algorithm. Second, algorithms help us optimize resources. By choosing an efficient algorithm, we can reduce the time a task takes and the amount of memory it consumes. For instance, if you're processing data from 1,000,000 users, a poor algorithm can cause your system to crash or respond slowly, both unacceptable in real-world systems. Lastly, algorithms are the foundation of all data structures and programming practices. Arrays, stacks, queues, trees, and graph all rely on algorithms to operate effectively. In short, kung walang algorithm, then walang software na magpa-function ng tama. Kaya nga kinakailangan i-define mo ng tama ang algorithm mo para maka-expect ka ng maayos na software. There are several proven strategies or techniques used to design algorithm. Let's briefly go over a few of the most important ones. First, the brute force method. This involves trying all possible solutions and selecting the best one. It's simple and guaranteed correctness, but it's often inefficient. A common example is the brute force solution to a password by checking every combination until the correct one is found. Para bang brute force na yung sa pin code, sa ilan ba yung pin code? 4 na lang. So, ibig sabihin, magsisimula ka 0000, then 0001, 0002, hanggang 9999, hanggang makuha mo yung tamang combination. So, parang dadaanan mo lahat ng possible combination. Yan ang brute force. Second is divide and conquer. Here, we break a problem into smaller sub-problems, solve them individually, and then combine their results. Merge sort is a classic example. It divides the list, sorts each half, then merges them together. Third is dynamic programming. Solves problem by breaking down into simpler, overlapping sub-problems. It remembers previous results to avoid repeated work. A well-known example is solving Fibonacci sequence efficiently. Next is we have the greedy algorithm. These make the best choice at each step, hoping to find the global optimum. For example, when finding change using the least number of coins, a greedy approach works well if your coin system is compatible. Once we design an algorithm, we need to evaluate its performance. So this is called an algorithm analysis. We generally analyze an algorithm based on two aspects, time complexity and space complexity. Time complexity refers to how long the algorithm takes to complete based on the size of the input. For example, if doubling the input size double the runtime, we might say it has linear time complexity. Space complexity refers to how much memory the algorithm uses while running. A sorting algorithm that needs to create new arrays to work might consume more memory than that sorts in place. Analyzing these two factors help us determine if an algorithm is practical and scalable. For small tasks, most algorithms will seem fast, but with large data, inefficiencies become obvious. To express time complexity, we use big O notation. It describes the upper bound of an algorithm's growth rate as the input size increases. Let's look at some common time complexity. First is the O1, or the constant time. The algorithm takes the same amount of time regardless of input size. For example, accessing an element in an array. O log n, or logarithmic time. So algorithms like binary search fall here. As input size increases, operations grow slowly. Then, On, or linear time. The time grows directly with the input size. A linear search over a list is an example. O and log n, or log linear time. More efficient sorting algorithms like merge sort and quick sort typically fall into this category. On On squared, or quadratic time, often found in simple nested loops like bubble sort, not efficient for large inputs. O2n, or exponential time. Algorithms solving problems like the recursive version of the Fibonacci sequence can fall here. And then On factorial, or the factorial time. This is extremely slow. An example is the brute force solution to the traveling salesman problem. Choosing an algorithm with better time complexity is crucial when working with large-scale data. Let's now turn to space complexity, which measures how much memory an algorithm needs to run based on the input size. Space usage can be broken into two parts. Fixed space, which means memory that doesn't depend on the size of the input. So for example, a few variables used to control a loop. Variable space, memory that changes depending on the input size, such as arrays, lists, or recursive call stacks. For instance, if you implement a recursive function without optimization, each recursive call may add a new frame to the call stack, increasing memory usage. Efficient algorithms strike a balance between time and space. Sometimes, you might use more memory to save time or vice versa. This trade-off is common in real-world applications. Now let's talk about one of the most common algorithmic tasks, sorting. Sorting is the process of arranging data in a particular order, usually ascending or descending. We use sorting to improve the efficiency of searching, filtering, and organizing data. Let me walk you through a few popular sorting problems. So we have bubble sort. This is one of the simplest sorting algorithm. It repeatedly compares and swaps adjacent elements if they are in the wrong order. Though easy to understand, it's not efficient for large datasets. Then the selection sort. This algorithm selects the smallest element and places it in the correct position, then repeats for the remaining elements. So like bubble sort, it's simple but slow. Then insertion sort. This algorithm works like sorting a hand of playing cards, taking one element at a time and placing it in the correct position relative to the sorted parts. It's efficient for small or nearly sorted datasets. Merge sort. This follows the divide and conquer approach. It divides the array into halves, sorts them recursively, and merges them back. It's more efficient and stable. And then the quick sort. Quick sort picks a pivot partitions. Quick sort picks a pivot, partitions the array, and sorts each part recursively. While fast in practice, its worst case performance can degrade the ON squared without careful pivot selection. Sorting is essential in database management, search engines, and even in how data is rendered in apps and websites. Now let's move to searching algorithm. Searching is the process of finding a specific item in a dataset. This could be a user in a database, a word in a dictionary, or a product in an online store. Two common searching algorithms are linear search and binary search. Linear search is the simplest method. It checks each element one by one until it finds the target or reaches the end, and it works well with unsorted data, but it can be slow for large datasets. Binary search is a much faster technique, but it requires the data to be sorted. It works by repeatedly dividing the search range in half. For example, when looking up a name in a phone book, you don't start at the beginning. You flip to the middle and adjust based on comparison. That's binary search in action. Choosing the right search algorithm depends on whether the data is sorted and how large the dataset is. Now we'll explore graph algorithms, which are used to solve problems involving networks. In computer science, a graph is a collection of nodes, also called as vertices, connected by edges. Graphs are used in social network, routing system, dependency graph, and more. Let's look at a few examples of graph algorithm. We have breadth first search or BFS. This explores the graph level by level, visiting all neighbors before going deeper. It's useful in finding the shortest path in an unweighted graph, such as finding the shortest route on a map. Depth first search or DFS. This dives into each branch before backtracking. It's helpful in exploring all paths, detecting cycles, or solving puzzles like mazes. Dijkstra's algorithm. This is used to find the shortest path in a weighted graph. For instance, Google Maps may use a version of Dijkstra's algorithm to suggest the fastest driving route. Floyd-Warshall algorithm. This finds shortest path between all pairs of nodes. It's more complex but useful in systems where you need every possible distance pre-computed, such as airline scheduling system. Graph algorithms are powerful tools that help solve real-world problems involving connections and relationships. To conclude, let's reflect on what we've learned. Algorithms are step-by-step solutions that drive every operation in computing. They take input, process it, and produce output. The quality of an algorithm is measured by its time and space complexity, which tells us how efficient and scalable it is. We also explored the different ways to represent algorithms through natural language, pseudocode, and flowcharts, each offering a different perspective in planning and understanding. By studying algorithm design techniques like divide and conquer, greedy methods, and dynamic programming, we learn to approach problems strategically. We look at practical applications too, from sorting and searching to navigating graph and network. All of these examples show us how deeply embedded algorithms are in everyday technology. As we move forward in this course, keep in mind, the better you understand algorithm, the more capable you become at solving real-world computational problems in a smart and efficient way. So that's it for Chapter 1. Thank you. So standby na lang kayo sa Chapter 2. Bye!
For more ICCT College's video updates, please subscribe and click the notification button.